speaking of Ken Coates, he's going to present our What's Up tonight. And that is entitled, listen for it. There it is, Oumuamua. What is it? So let's hand this over to Ken. And do you want to use the hand mic or do you want to use
All right, can everyone hear me okay? All right, so I'm Ken Coates, and I'm giving a talk tonight on Oumuamua. Is it an alien spacecraft or just an asteroid? So these are the topics I'm covering tonight. So first off is, what is Oumuamua? Again, is it an asteroid from another solar system or is it an alien spacecraft? Number two is, can we visit it? Then we could find out. If we see aliens, we know it's an alien spacecraft. And what can we do to visit the next one? If we can't make it to this one, there's going to be another one. So let's see what we can do to get ready for that. And I'll finish up with what the latest is on sending a probe to our another star. All right, so the first thing about Oumuamua is how to pronounce it. So we're going to practice that. So I have the phonetic spelling there. So it's Oumuamua. All right, very good. So Oumuamua is a Hawaiian word for a messenger from afar arriving first. So since it came from another solar system, and it's the first one that we noticed, I think it's a very appropriate name. So whoever selected that is good. It has a scientific name, but I'm not going to tell you that one because it's too boring. All right, so it was discovered on October 19th, 2017 by Pan-STARRS, which is run by the University of Hawaii. It's the NASA's Near Earth Object Observation Program, and it finds and tracks asteroids and comets in Earth's neighborhood. So in case one of them hits us, this would be our first line of defense to find out who's coming at us, or rather what is coming at us. When it was first observed, it was thought to be a comet, but once the trajectory was known, it was determined that it was the first object that we've seen from another solar system, from another star to visit our solar system. So on this diagram, the green line, it looks like a V, that's the trajectory of Oumuamua. And this little ellipse on the left here is a kind of a typical path of a comet. So a comet is in a highly elliptical orbit and goes out and comes back. All right, so first thing I'm going to talk about its basic characteristics and why it appears to be an asteroid. The upper right photo is the best picture that we have of it. So as you can see, we don't know that much about it. That was taken by the Gemini South telescope in Chile. From its trajectory, it's clear that it came from another solar system. So there's really no dispute about that. It didn't come from planet X or something like that. So, and it came from the direction of the star Vega. But when it was at the location of Vega, which is about 300,000 years ago, Vega wasn't there because it was at a different place in the sky. So it didn't actually come from Vega, but just coming from that direction. So we don't really know what solar system it came from at this point. It's traveling about 59,000 miles an hour, and that's 26.4 kilometers per hour. And for a comparison, a comet that's far from the sun travels about 2,000 miles an hour. And when it gets close to the sun, it can speed up to upwards of 100,000 miles an hour. So it's about the range, same velocity range as a comet, but it's coming at such a steep angle that it's not going to be captured by the sun. And the brightness, one thing unusual about it is the brightness varies by a factor of 10. So that's really unusual. We don't see that in other objects in the solar system. It's been determined that the cause of that is that it's highly elongated. So it's about 10 times as long as it is wide, and it's tumbling. That's what's causing the variation in the brightness. As it's completely inert. No dust was observed around it while it was it was coming by. So it has a reddish color, which is similar to other objects in the outer solar system. So this picture in the lower right is a artist's conception of what it might look like. So it has a reddish color. And these properties suggest that Oumuamua is dense, composed of rock and possibly metal, has no water or ice, and its surface has been reddened due to the effects of irradiation from cosmic rays over hundreds of millions of years. Okay, so that's what we know about it as far as it being an asteroid. Now, what do we know about it being an alien spacecraft? Okay, so again, first is the unusual shape, because again, we don't see objects like this in our solar system. The most elongated object that we've found so far is an asteroid called 216 Cleopatra with a K. And that has about a 3-to-1 aspect ratio. But it looks like a dog bone shape. We don't have a close picture of it, but most people think it's a contact binary, so it's not even a solid object. So to keep something like that solid tumbling, it takes a lot of cohesion. Second, the other thing that's interesting that we didn't expect was that as it passed around the sun, there was more acceleration that can be attributed to the gravity of the sun. And there was no visible outgassing like you would see with a comet that could provide extra propulsion. So those are things that aren't explained at this point and could lead you to think that maybe it is an alien spacecraft with some kind of propulsion system. So we'll talk about what alien kind of spacecraft it might be in a minute, but let's go back to why it's not an alien spacecraft, because there's the no visible outgassing started scientists scratching their heads. What could cause propulsion that we can't see? So one theory that's come up in the last year or two is that it's made of nitrogen ice. And we have seen nitrogen ice in our solar system. When we visited Pluto in 2015, there are big sections on the surface of Pluto. This is a picture of Pluto that are composed of nitrogen ice. There's also water ice there too, but there's also nitrogen ice. So the theory is that it's a big chunk of a Pluto-like planet that got blasted off somehow from another solar system and came towards us. And there is some spectra that was taken later after its first discovery that indicates it may have some ice on it. So unfortunately, though, there was no change in rotational speed. So as it's coming around the sun, if its nitrogen is sublimating and going into a gas, you would think it would change the rotational dynamics of what it's doing, but we didn't observe that. So that's another big question mark. But so the question is, what kind of spacecraft would cause that, or would be consistent with these phenomena? So before I get into that, though, I'm going to call on Carl Sagan to remind us that extraordinary claims require extraordinary evidence. So that's the best reason why it's not, at this point, why it's not an alien spacecraft. Okay, so one thing that's consistent with what we've observed is it could be a light sail. So this theory was first proposed by two scientists at the Center for Astrophysics at Harvard, Shmuel Bialy and Abraham Loeb, and it's consistent with the acceleration because the light from the sun would propel the light sail, and it's also consistent with the brightness changes because a light sail has a very high aspect ratio. So we've flown 3 light sails so far. This is a artist's conception of the Planetary Society light sail that's still orbiting the Earth. It's been up, I think, at least three years or so. And the Japanese Space Agency launched a light sail in 2010 that's now orbiting the sun. And NASA launched a very small light sail just to do some testing, but they haven't done a lot of work with that yet. So I'll be talking more about light sails at the end of the talk when I discuss how we can send a probe to another star. But again, I'm mostly with Carl Sagan on this. And just if you don't know that much about this object, it's pretty hard to come to a conclusion that it's an alien spacecraft, because that seems unlikely, but you never know. Okay, so how would we answer this question? The most obvious one is visiting Oumuamua, and Alan Hibbard, who works for the Initiative for Interstellar Studies in the United Kingdom, he's a software engineer, has proposed a mission to get to Oumuamua. It would launch in 2028, and it would do a gravity assist from the Earth and Venus, not using a lot of fuel at those planets. But when it got to Jupiter, it would use all of its fuel to get the most speed out of it, and it could get up to 82,000 plus miles per hour versus the 57,000 that Oumuamua is going. So it would catch up by the year 2054. So he has submitted, or his institute has submitted a proposal to the NASA Decadal Survey for this mission. That's a survey every 10 years. They decide what are the big science priorities for the next 10 years. So it's possible it could get funded. Who knows? But let's assume it doesn't get funded. That's the most likely thing. So how about getting ready for the next one? So scientists have estimated that at least one of these objects per year is coming through our solar system. Now they're kind of dim, so you have to be looking for them. Pan stars is probably a good way to look for them, but maybe there's other ways. So let's figure out how we can get ready for the next one, because we always talk about sending probes to other stars. Here's a part of another solar system coming to us. It's a lot easier to go visit that than go to another star. So let's make this a priority. Okay, so the same institute that had the mission to go to Oumuamua has proposed a spacecraft that can use the solar Oberth maneuver. So that's the maneuver where when a spacecraft falls into the gravitational well of a planet or a star, and then uses its engines to accelerate, you end up getting a lot more velocity out of your propellant than you would if you're just going at a slower speed. So you're actually stealing some energy from the bigger body, which wouldn't really miss it. And that's a way to get up to a really fast speed. So instead of using Jupiter, with the Oumuamua, it was too far away. It's already as far out as Saturn. So we couldn't really use the sun to get to Oumuamua. But since the sun is has so much more mass than Jupiter, it's better to use the sun, and you can get going a lot faster. So of course the sun is really hot, so you need to have a super heavy-duty heat shield, and that's what this proposed spacecraft would have. Now we have some experience with that. The Parker Solar Probe's heat shield seems to be working pretty well, so we could use something like that possibly. Okay, so let's just to finish up, I'm going to talk about the latest on our efforts, as meager as they are, to visit another star, and it's the name of the project is called Breakthrough Starshot. If you may recall, in the last few years, two of our main speakers have discussed this mission, talking about how the most interesting one to me was how the little sensor would work. The sensor weighs 1 gram or something, and gets all the way to Alpha Centauri. So it would use a solar sail propelled by lasers to get up to 20% of the speed of light. And it would take about 20 years to travel to Alpha Centauri, so it'd be in the lifetime of a investigator, so that's always helpful. And it would carry a small probe to collect data and beam it back to the Earth. So a solar sail would be susceptible to interstellar particles that could destroy the sail. So it would make sense to send as many as we can afford in the hopes that at least one of them would work. One of the biggest challenges, though, would be building this giant laser array. So it could be built on the Earth, or it could be built orbiting the Earth. So each one has advantages and disadvantages. So since those talks we had a few years ago, not really much has happened. It's still really a conceptual design. But I did find a fairly recent video of how it would work. Let's see if I can switch to that. Let's see. Is this working? I think I have to reshare. Let me stop sharing. Then if I reshare, then I can share a different application. Yeah. Okay, there's no sound on this video, so there's nothing wrong with your sound. So this is the laser array. Now here's the spacecraft the light cell being ejected from a spacecraft that took it into orbit. And it's waiting for the lasers. So it looks like maybe 200 maybe. So just make sure you're not flying right above that. And then here's the second one. This is the idea that you want to send a bunch of them. You build this big laser array, you may as well send as many as you can. The light sails themselves probably don't cost that much. It's all about the lasers. So now it's leaving it. That's leaving the sun. There's the sun. It's going away on its mission. It's passing by planets. That might be Saturn there. I'm not sure. And there's the distant sun. There's Alpha Centauri. 20 years later. And there's a very convenient ocean planet right in our path. So, hey, I think we can move there tomorrow. So take some photos and hopefully, does a few other things like check. I'm not sure what else I could check for quickly, but then it looks like it's going to use some lasers to send the data back. So there's the data packet going back 4 light years past all the planets back to Earth. And it looks like the proposal is that it's going to use the laser array as a receiver, because by the time it gets back to Earth, the power of that signal is going to be very low. So you need a bunch of satellite dishes to collect the data. So. All right, so let's go back to the presentation. Well, okay, so that's the end of my presentation. And thanks for listening, and I'm happy to take any questions.
You can. That was wonderful. Great.
These things that are coming, could they just be probes from somewhere? Not
Do you want to
actually
use the microphone?
manned?
Well, for the people on Zoom, why don't you come up and use the microphone, please?
Don't be shy. Or I can come over, but if I do that, I'm liable to get feedback over there. Don't worry.
I was just asking if those could be probes.
Yeah, so in other words, if we send a solar sail to Alpha Centauri, we're the aliens sending the probe. So sure, it could be a probe from another civilization. There's also a famous book by there's a famous book by Arthur C. Clarke called Rendezvous with Rama, where something that looks sort of like this comes through our solar system. Inside is like a zoo, and every solar system that had the technology added some animals and other species to this zoo inside, and so that's it.
Could these be related to UFOs?
Possibly, but I'm skeptical of UFOs because if you have the technology to visit another star in person, why hide?
No, they're probes. The UFOs are just probes.
Oh, just probes.
Yeah.
Well,
No, they could be.
I'm skeptical of UFOs in our atmosphere. Any other questions online or anything, or
Let's see. Let me check on here.
see if there's something in the chat?
Whoops, that was me. Sorry about that. Here we go. Shape of a soap bar is easily explained. Well, that's interesting. Let's see what else. Yeah, well, that's it so far.
Okay, a soap bar. So aliens tell us that we need to take a shower and clean ourselves up because we're messing things up too much. That's possible.
Yeah.
All right. Well, thanks a lot.
Okay, thank you. Thank you, Ken. And now we're going, Tom, are you with us?
Yep, I'm here. Just let me get things
Uh,
rolling.
we're gonna start this off again. So tonight's talk. Do I need to talk louder? Okay. Come on, guys. Where am I at? Red? Oops. Is that a little better? Okay. All right. This is a talk entitled Planetary Defense and NASA's DART Mission. You may have seen a little write-up I did last October on it. So tonight I'm pleased to introduce Dr. Tom Statler. Dr. Statler works in the Planetary Defense Coordination Office and the Science Missions Directorate Planetary Science Division at NASA headquarters in Washington, D.C. That's a complicated sentence. And is program scientist for the Double Asteroid Redirection Test, the Lucy mission to the Trojan asteroids, and the Japan-led MMX mission to the moons of Mars. Dr. Statler earned a bachelor's degree in physics and astronomy from the University of California at Berkeley, and a PhD in astrophysics from Princeton University. Before joining NASA in 2014, he spent close to 30 years as a researcher and professor, his work encompassing a broad range of topics from collisions of multiple universes and the structure of galaxies to the spins and orbits of near-Earth asteroids. In fact, asteroid 9536 Statler is named in his honor. He's also a composer and conceived the Lucy Soundscape project, in which NASA has invited composers worldwide to share original music inspired by the Lucy mission. And now please welcome Dr. Statler.
Thanks, and hi, everybody. How's my sound?
It's good on Zoom.
All right, great. I'll assume everybody can hear me unless someone stops me. Great to be with you. I'm a Bay Area kid. I grew up in Los Altos, and as you heard, I went to undergrad at UC Berkeley, so it's great to be virtually back in the Bay Area tonight. So glad you started off the evening with a little talk about Oumuamua, one of the fascinating small bodies that went temporarily in our solar system. I love all the small bodies in our solar system, the comets, the asteroids. They're all fascinating. And as I'll show you in a few minutes, the solar system of small bodies that we're living in is not really the one that a lot of us grew up thinking we were in. When we were all kids, probably most of us, the textbooks that we read said there are a small number of asteroids, probably more than we know about. And that picture has changed substantially over the years. And of course, also we've begun this fantastic exploratory era where we're able to send robotic spacecraft to asteroids and comets to orbit them, to touch them, to interact with them, and to bring samples back for analysis in the laboratory. And so we're really entering a new golden age in our understanding of the small bodies in our solar system. And one of the things that we've come to understand is that there is no such thing as just another asteroid, because asteroids formed in different places in our solar system. They represent the leftover raw materials, the leftover building blocks from planet formation. And each one encapsulates a little different part of the history of our distant past, the history of our solar system. Every once in a while, we also have one that maybe is encapsulating part of the history of a different solar system, and that's a different story. But tonight I want to talk about a very specific subset of asteroids. Those are the near-Earth objects, and in particular, the potentially hazardous asteroids, because asteroids orbit the sun like the planets do, and most asteroids are not orbiting close to the orbit of the Earth, and so they're never dangerous. But there is this natural hazard living as we do on a planet that orbits a star, and that is that there are other bodies in orbit around that star, and there are asteroids that whose orbits bring them into close proximity with Earth, and those can pose a natural hazard, occasionally a national hazard as well, but a natural hazard because collisions have always occurred and will continue to occur. So that's what planetary defense is. Planetary defense encompasses all of the activities that are involved in understanding that natural hazard of asteroid impacts, finding the potentially dangerous objects, characterizing them, making plans for what to do if one is genuinely a threat to us, learning how to mitigate that threat, and to assess how well we do it. All of these activities are part of what we do in the Planetary Defense Coordination Office at NASA, in conjunction with university researchers, observatories, public and private observatories, other nations as well, federal agencies, state emergency management agencies, and the International Astronomical Union's Minor Planet Center, which NASA funds. In particular, tonight, I'll give you a quick overview of several of these activities and focus then in the second half of the talk on the DART mission, which is really and truly happening right now. We are genuinely sending a few $100 million worth of spacecraft to intentionally crash into an asteroid and destroy itself, but for good purpose. So here's what I meant when I said the solar system we live in doesn't look like the solar system that we thought we lived in when we were growing up. This is the number of near-Earth asteroids known as a function of time from 1980 to the present, or at least a couple of months ago. I didn't update this slide for tonight's talk. And this is, you can see that if you go back only about 20 years, there were under 1,000 asteroids known that can come into near-Earth space. And now that number is 30,000. In the last couple of months, I think we've just edged over 30,000 asteroids known. Now, if you look at the colors in this plot, a lot of them are very small. And so there are multiple stories to be told here, but it really does highlight the degree to which these efforts of asteroid discovery, almost all of which have been managed and supported by NASA, have really changed the complexion of the way we perceive our solar system. Now, if we divide this up just a little bit, I'm going to skip that plot and show you this one. So this is a plot of discoveries by year. It's number of discoveries each year. It's color-coded according to the particular observatory telescope that made the discovery. And I'm not going to go into that right now. But this is the plot for big asteroids. Things that are bigger than a kilometer. Things that if they did hit the Earth, it would be globally catastrophic. At least many people and animals and plants would be killed. Could be a mass extinction. Anything could happen. And you'll see that the discoveries of objects that are larger than a kilometer peaked fairly soon after we started this concerted campaign to discover near-Earth asteroids, and has been tailing off ever since. And the total number is really topping out at around 900. And you could, if you think about what's happening, you look at this plot, it's fairly clear that the reason they're topping out at around 900 is that that's all there are. We really have found almost all of them, because as the number of discoveries in this plot climbed and then tailed off, what was also happening at the same time is our ability to find near-Earth asteroids was getting better and better and better. Our telescopes were getting more and more sensitive. So when you get better and better ability to find things and you find fewer and fewer of them, that's telling you that you really have found just about all of them. So this is one way in which our lives now are fundamentally different from what they were 30 years ago, and yet we probably didn't even notice it, most of us, that 30 years ago, if I were giving this talk and you had asked me, Tom, do we have any certainty that we won't be wiped out next Tuesday by a 10-kilometer asteroid that wipes out all life on Earth? 30 years ago, I would have had to have said, no, we have no idea. I have no idea whether we might be wiped out by a giant killer asteroid a week from Tuesday. Now, I know that we will not be wiped out by a giant killer asteroid a week from Tuesday or anytime soon, because none of these objects is in fact an impact risk to the Earth. And so that particular risk of ignorance has changed. It has gone away. It's been retired because of our efforts. Maybe if, I don't know, if you're building the time machine in your garage and you perfect it, you can go back in time and tell people 30 years ago that it's okay, they don't have to worry, and they don't have to make all those lousy movies like Armageddon, because there really wasn't any danger. But that's another topic. Now, the situation is different if we look at the asteroids that are smaller in scale. And this is everything that's bigger than 140 meters. It's the same plot, the number discovered per year. And 140 meters is sort of a fiducial number that we use in the sense that things that are smaller than 140 meters, if they were going to hit the Earth, the best way to mitigate that might probably be just to evacuate people from the region that's going to be impacted, because the effects would be fairly localized. But above a size of 140 meters, this would be really regionally destructive, and you would want to do something about it if you could. And you can see the number of discoveries of these objects is still going up day by day. We are still finding more and more of them. So where are we in this process? NASA has a congressionally mandated task to find and determine the orbits of all of the near-Earth asteroids bigger than 140 meters. This is a very, very large task. It was an underfunded mandate, and so NASA did not hit the time limit that was established by Congress, but we're well on our way. But this is about where we are. Roughly, we think we've got about 40% of these objects found, leaving about 60% of them not found. And while there is not a single known asteroid that is an impact threat to the Earth, that doesn't mean that there isn't an undiscovered object that might be. So we know that no known object is going to impact the Earth anytime soon. Our concern is with the asteroids that we haven't yet discovered, and that's why we have to continue to do this work. Oops. Just as a quick example of what we can do now with our modern observatories and systems and networks, a few years ago there was an object discovered by the Catalina Sky Survey in Arizona that was discovered to be on an impact trajectory. It was discovered 8 hours prior to impact. In those 8 hours, additional observations were obtained from the Atlas telescope in Hawaii. And as a result of those observations, it was possible to first lay down a swath of possible impact sites. That's that first blue line on the left-hand map. And later on in the same day, to pin down the projected impact point of that small asteroid to southern Africa. In fact, there was a bolide detected over Botswana that evening, and there was even security camera footage taken on somebody's property that showed the asteroid coming in. I think the video is running. Yeah, there it is going down over the horizon. And US government sensors that are intended to detect other kinds of unauthorized explosions in the atmosphere pinned down this event, the impact of 2018 LA in Botswana. So this is an example of how it is now possible to actually find objects and identify them before they impact the Earth, which has never been possible before. It's part of our developing capabilities, which we're making better and better all the time. Oh, and the other fun part is teams went out and actually found the meteorite fall resulting from that asteroid strike, which is great. Now, this is a much, much smaller object than we're really tasked to warn about. I think this was maybe only a 5 or 10 meter body, but it was a great opportunity to exercise our capabilities. And it was the third case in which an object had been found and an impact calculated before it occurred. And actually, just in the last few weeks, you might have heard there was a fourth one, a small object that was discovered just a couple of hours before impact that broke up in the atmosphere in the Atlantic Ocean a few hundred miles north of Iceland. So now there are 4. But I want to hit a little bit about how this is, how planetary defense involves more than just, a bunch of astronomers at telescopes. Because as I said, NASA has a mandate from Congress to do this work. And this involves other agencies across the federal government in the US, as well as other governments. There is a National Near-Earth Object Preparedness Strategy and Action Plan that was in development for a number of years. It was finally released in 2018. And more recently, there is the United States Space Priorities Framework that says, as a goal, the United States will lead in cooperation with commercial industry and international allies and partners in efforts to enhance warning of and mitigation against potential near-Earth object impacts. So this is something that can happen. It doesn't happen often, but the potential for a very serious event is large enough that we want to understand it and want to do something about it, especially because in the array of natural disasters that we do face living on a planet, asteroid impact, at least right now, asteroid impact is the only potentially preventable natural disaster. And if we can prevent it, we want to learn how. I will just skip over this. Just to say that involved in this action plan is an interagency working group that pulls together lots of federal agencies. You'll see the Department of Commerce, the Department of Homeland Security, specifically through FEMA, the Federal Emergency Management Agency, and these other agencies. And we do work together with the other parts of the government to figure out, in the event that there is an actual emergency, who would do what, who would notify whom. And there is actually a flow chart for the impact notification process if we do discover an object that is actually an imminent impact threat to the Earth. I won't go through every step in this, but you can sort of walk yourself through the flow chart, excuse me, at the left-hand side, as it's gradually determined whether there is a serious problem. But once it's determined that there is one, there's a notification from the NASA administrator up the executive branch to the White House. There's another branch of NASA that informs Congress. Other agencies are informed. If there's a potential impact in another country, the State Department notifies those other governments, and then we notify the public. I do want to emphasize, though, that if you go back all the way to my first slide, which I won't go back to, everything that we do is coordinated in terms of data through the International Astronomical Union's Minor Planet Center, which means that all of the observational data on asteroids is all public from the moment it's first available. So everything is there, and any interested person can find the positional data on asteroids, can find the latest orbital computations, and do their own calculations if they want, because NASA always makes all of the data public, free of cost to the entire world. Now, bear with me just one second, because I want to skip over to DART, which happens to be in a different PowerPoint file. All right, looks good on my screen. I hope it looks good on yours. So now I want to skip over and talk about the Double Asteroid Redirection Test. This is going to be a historic event for many reasons. First of all, it's our first full-up test. Excuse me one second. Our first full-up test of a real asteroid deflection technology applied to a real asteroid. And also, in the broader sense, it is humanity's first attempt to actually change the motion of a natural celestial body in space. It really is a historic thing. But I do want to emphasize from the start that the Double Asteroid Redirection Test is a test. There is no emergency, regardless of what you might read now or in the future in the tabloids or on the internet. There is no emergency. There is no known asteroid that poses an actual impact risk to the Earth. The current impact hazard comes from, as I said before, the asteroids that we don't know about yet, the asteroids that are not yet discovered. And since we're discovering asteroids every night, it could happen, it could come to pass that someday we do discover an asteroid that is actually an impact threat to the Earth. And that's why we're conducting this test now, to develop the capability, to develop the understanding in case we ever find ourselves in a situation where we need it. So what we're doing in DART is we are testing the technique called kinetic impact. Kinetic impact is a technical term for run into the thing as hard as you possibly can. And so that's what we're doing. We've built a spacecraft called DART that has one instrument on it. It's a camera. It has a lot of sophisticated software to autonomously guide itself and navigate to a direct intentional impact with a small asteroid called Dimorphos. Now, Dimorphos is the smaller member. It's a moonlet in a binary asteroid system called Didymos. The main asteroid Didymos was discovered first. Shortly thereafter, it was determined that it was a binary. Didymos is about 800 meters in diameter, and about not quite 2 kilometers away from it is the asteroid Dimorphos, which is about 160 meters across. So kind of the size of a high school football stadium is Dimorphos. It's about half a mile away from Didymos, and it is in orbit, held in orbit by the weak gravity of the larger asteroid Didymos. Dimorphos goes around Didymos at the astonishing rate of 7 centimeters per second, completing an orbit every 11 hours and 55 minutes. Now, the reason we're doing this test in a binary asteroid is that by hitting the asteroid with the spacecraft, we can't change its motion very much. And indeed, if we were going to use a kinetic impactor as a real asteroid deflector on a real dangerous asteroid, we would not change its motion very much at all, because the essence of planetary defense is to discover these dangerous objects early, so that a fairly small push just built up over many years causes the asteroid to simply miss the Earth at the time of impact. I should back up just a little bit, just to paint the picture. Of course, the Earth is going around the sun. Asteroids are also going around the sun. And an asteroid isn't dangerous unless there's an actual intersection between the Earth's orbit and the asteroid's orbit. And even then, nothing bad happens unless the Earth and the asteroid try to get to that intersection point at the same time. So what we're trying to do in planetary defense is not blow up the asteroid or destroy it, but nudge it years in advance, just so that we delay it, or actually turns out to be, in most cases, easier to make it arrive a little bit early. And so if we make the asteroid arrive at that intersection point 10 minutes early or 10 minutes late, then it misses the Earth and everybody is happy. So that's how we would consider using a kinetic impactor as a deflector, how we imagine doing it if we succeed in discovering dangerous objects early. Since the nudge is small and we want to test this technology, we want to do this in a system where we can easily see what we did. And that's why we choose a binary asteroid system, because the nudge that the DART spacecraft applies to Dimorphos changes its orbit around Didymos ever so slightly, but enough to be able to measure, because we're expecting something like a 1% change in the period of the orbit. So it might go from 11 hours and 11 hours and 55 minutes to 11 hours and 50 minutes. And that means that this clock has been going like clockwork every 11 hours and 55 minutes starts running fast. And that's something that we can detect down the road. And I'll get to that in a couple of minutes. DART has been many years in development, and it's really kind of amazing to us who have been working on it and seeing the spacecraft being designed and built over the years. It's kind of amazing to realize that we've got a spacecraft in space now. And in fact, it's only 6 months until it's destroyed on the surface of the asteroid, which will be sad and wonderful at the same time. But here's the DART spacecraft being built in the lab at the Johns Hopkins Applied Physics Lab, a little bit north of where I am. I put this in so you can see for scale. It's not a very large, spacecraft. It's only a couple of meters across, weighs about half a ton. But it will be moving at about 15,000 miles an hour when it hits Dimorphos, and carrying a lot of momentum and a lot of energy when it does that. We transported the spacecraft from the East Coast to the West Coast to Vandenberg Space Force Base in a truck. That's how you move a spacecraft that don't need to go in an airplane. And then it was put together with the launch hardware at SpaceX's facility at Vandenberg. I like showing this picture because that silvery thing down at the bottom of the spacecraft is the aperture door on our camera called Draco. That's the one instrument. That is the thing that will guide us into the asteroid and will return many wonderful images on kinetic impact day. Here's DART being integrated into the payload fairing, the nose cone of the launch vehicle. You can see that fairing could accommodate a much larger spacecraft. So we're not occupying a lot of the territory inside, but there's DART and there's a person. The last view anybody ever had of the spacecraft on Earth. I was there for the launch. I was lucky enough to be there, and we had a wonderful tour of the integration facility by the SpaceX staff. That's me in the blue shirt. And right next to me, to your right, is my boss, Dr. Lori Glaze, who's director of the Planetary Science Division at NASA headquarters. And there's our rocket behind us, and that was the same right there. That's the same nose cone fairing that I was just showing you. And I'll just go back and forth just a little bit. Just take a look at how that fairing opens up, or in this case, closes up, and you can see the seam on this view. Hold that in your heads, because you'll see that from the inside in space in a few minutes. We got a wonderful view of the facilities. There was our rocket on the launch pad. There was a launch on the night of November 23rd, just a few months ago. And it was really beautiful and really very exciting to be there. I decided that it'd probably be best not to try and show a long video over Zoom, but there is video of the launch, and the NASA TV launch broadcast is available on YouTube. So you can look that up if you're interested. I grabbed a couple of stills from the video. Here's the first stage separation. The picture on the left is looking out the top of the first stage. The bright spot is the second stage engine that has just ignited, and the view on the right is from the bottom of the second stage, looking at the nozzle. Sorry, couldn't find the word. The nozzle of the second stage engine. That's the view from inside the fairing as it's separated. So this is, I don't know if you can see my cursor, but up at the top, that's the inside of one of the halves of the fairing. The other half you don't see. And over on the left-hand side, you see the spacecraft, and the thing that looks like a pizza tray is the high gain antenna on the spacecraft. A few minutes later, SpaceX landed the first stage of the booster on the barge. Of course, I Still Love You, great name for a barge, down south of LA. We had some time to wait. So that's me being interviewed on NASA TV. So if you watch the launch broadcast, you'll see me doing that. That's what that looks like in actuality. Somehow the interviewers always stand on boxes. So give credit for the ladies who do those interviews, because a lot of them are standing on boxes. And this is the great shot that made everybody very excited. This is the view from inside the second stage, looking at the DART spacecraft being sent off into space on its own. So that was a wonderful moment for the whole team. So here's what we're doing. I hope you can see this animation. Earth is going around the blue circle. Didymos, the asteroid, is on the extended circle. And here's the moment where DART launched in November. DART follows, it's the little yellow dot that actually follows fairly close to Earth, dips down below the ecliptic plane, below the Earth's orbit, to meet up with Didymos this coming September, when everybody is close together and we can have high bandwidth communication with the spacecraft and good telescopic observations of Didymos at and around and after Kinetic Impact Day on September 26th. Now, how are we going to do this? Because some of you have probably noticed that following kinetic impact, we have no spacecraft left with which to observe the asteroid, and this is true. But we've been studying Didymos system for years with telescopes from Earth, and it is an eclipsing binary because it's oriented in the right direction. And so astronomers know about eclipsing binaries. Some of you guys might actually be associated with the AAVSO and IOTA for occultation observations. So you know about this, that you can't see using a telescope on Earth. You can't see the two bodies resolved. You just see the total light from the two of them, but you see a dip in the total brightness when one body goes behind the other. And it's those observations that told us in the first place that Didymos is a binary and tells us exactly what the orbital period is, because we've observed those eclipses over and over and over again for years. So what we will do following impact is just exactly what we've been doing. We'll continue observing those mutual events, those eclipses and transits, and watch over the weeks and months following impact that the clock is running a little bit fast, that those things don't occur on schedule every 11 hours and 55 minutes. Actually, it'd be half that because you get one in front and one behind. So 6 hours and 57.5 minutes. 5 hours and 57.5 minutes. They're off schedule, and that is the measurement that tells us how much we actually deflected the asteroid. DART has these mission requirements. The first one, to hit the asteroid, impact Didymos, to change the orbital period, to measure the period, and also measure an efficiency factor that I'll tell you about in a couple of seconds. And the noteworthy thing about the DART mission, which is really different from just about every other mission that we've conducted, is that the first of those requirements is met during DART spacecraft operations. following impact, there are no DART spacecraft operations because there is no DART spacecraft left, but there are still 3/4 of the mission left to be done. So, so the mission is barely even half done at the time when the spacecraft is destroyed. And come kinetic impact day, when we finally have loss of signal, we get the last image, we have a loss of signal confirmed from the spacecraft, there will be a great big cheer that goes up from the engineers, but the scientists will be saying, wait, we're only half finished, because anybody can take a few $100 million of spacecraft and smash it into an asteroid. But the real question is, did we deflect the asteroid, and how efficiently did we do it? And that's the whole second part of the mission. And that hinges on this thing called beta, which is the momentum transfer efficiency. Because remember, I said the spacecraft is running into the asteroid at a speed of about 15,000 miles an hour. Why? You could build a bigger spacecraft and just have it bump into the thing and carry the same amount of momentum. But it's not all about the momentum, because when the spacecraft hits at that high a speed, the kinetic energy, the energy of motion that it's carrying, is much, much larger than the same amount of mass of high explosive. So it's the energy that also matters. And that energy will dig a crater, it will crush the spacecraft, probably vaporize some material, will dig a crater, and there will be a blast of ejecta coming out back along the direction that the spacecraft came in on that looks like an instantaneous little rocket engine, giving the asteroid an additional push. But we don't know how real asteroidal materials are going to react to that kind of an impact. And that's really the central reason why we need to do this test, because it could be that not very much happens. If the spacecraft runs into the asteroid and there's no ejecta coming out, then all we get is the push delivered by the spacecraft itself. If the surface is a little bit more responsive, let's say, and we blast out some material, that's an extra push. And if it's very responsive and blasts out a lot of material, then we might get a bigger push on the asteroid from the recoil from that ejecta coming out of the crater than we deliver by the spacecraft itself. And that's why kinetic impact at a high velocity is potentially a really useful deflection technique, because it's not just the spacecraft that runs into the asteroid, it's how the asteroid responds. And that's why we need to do the test. So we're not quite halfway there. We launched about 4 months ago. We're 6 months away in cruise. Mark your calendars for Monday, September 26th, 4:14 in the afternoon your time. You might have to get off work early, run home, turn on NASA TV, or turn it on your computer or your phone to watch what's going to happen. It's going to be very exciting, because the Draco camera will be live streaming back images once per second. And I didn't have time to go into everything that's going to happen on Kinetic Impact Day, but it won't be until the last hour that we actually see Dimorphos, the target asteroid, in the camera, in the field of view of Draco, of the DART spacecraft. And in that last hour, it will gradually, at 1 image per second, get bigger and bigger and bigger. And only in the last few minutes do we get to see what Dimorphos actually looks like. That's actually what makes the mission hard, because the engineers have had to program the flight software to be able to target something of an unknown shape. We don't know what it looks like. We don't know where the shadows are going to be. We could get very unlucky and have some weird shape that casts a strange shadow, and it could be very hard to tell exactly where the center of the body is. We hope that doesn't happen, but it is a risky endeavor. It's not an easy thing to build an autonomous spacecraft to hit a small asteroid that you have never, ever seen before. And I'll just say one more thing before I close and close my talk and open up for questions. If you look really carefully down at the bottom right, there's another little spacecraft there. I'll try and point at it if you can see my cursor down there. And that's a little guy called Lychee Cube, a CubeSat that's contributed by the Italian Space Agency. Lychee Cube is going to be deployed. It's riding along on the side of DART. It's going to be deployed from the DART spacecraft about 10 days before the impact. It'll offset itself to the side and behind and follow DART in about 3 minutes behind with its cameras running to capture the moment of impact and the plume of ejecta that comes off. It will try as hard as it can to pan around as it passes the asteroid, see the impact plume from the other side, and Lychee Cube will do something that DART can't do, and that is image the backside of the asteroid so we know the complete volume of the object that we hit, and that's going to help in the data analysis. So I haven't told you everything there is to know about DART. If you want to know more, you can go to nasa.gov/DART. There's lots more to learn. I hope you'll get interested in this, and I hope you'll be with us watching NASA TV on Kinetic Impact Day. Thanks for listening. Happy to take any questions you've got.
Thank you, Tom. Anybody have anybody here? No question? Oh, good. Ken's got one.
I have a question. I don't remember what year it was, but there was a mission called Deep Impact that also impacted asteroid. Could you compare this mission? I understand that this mission has different objectives, but how did that mission inform this mission?
So yeah, Deep Impact. Question was about the Deep Impact mission from I don't want to guess when that was. It was a while ago. It was probably about 15 years ago. That was a completely different mission. The only thing it had in common was that there was an impactor. So this was a mission, Deep Impact was a mission to a comet, not an asteroid. And the comet was quite a large body. It was much larger than the asteroid that we're targeting. And the purpose of the impactor was not to change its motion. It was just to kick up a whole bunch of stuff that could be analyzed. So that the impactor separated from the main spacecraft, went in, impacted, kicked up a big plume of stuff that was observed by the main spacecraft to do a chemical analysis, dust analysis, and all that. So that mission was all about understanding the composition of comets, a different thing entirely. And that impactor, if I remember right, was quite a lot smaller. I think it was about 40 kilograms. So different impactor, different purpose.
There you go.
So on September 26th, what's the best way to get the news? Just go to nasa.gov/DART. Is that?
Yeah, there will be, if you just watch the NASA website, just nasa.gov, or look at the NASA feed on Twitter or social media, there will be a lot of news as we get close to it. We're still working out exactly what we're going to do, exactly how long the broadcast is going to be. You can always get NASA TV from the nasa.gov website. I'm not sure what other feeds there might be. It's all, we're all still in the planning stages of exactly what we're going to do and what we're going to be showing, but you can be sure it'll be on NASA TV. Some of the streaming services have NASA TV on streaming TV, but you can always get it through your home laptop.
Oh, come on. Sure.
So my other question is there any dead weight on the spacecraft, or is it all useful weight? I mean, just to
yeah, so
mass to make a bigger impact.
That's so that's an interesting point, of course, because most of the time you're trying to make your spacecraft as light as possible because you want to put it, well, for all kinds of reasons, you want to make it as light as possible so you can launch it. In our case, having more mass is a good thing. There was no extra mass put on the spacecraft simply for the purpose of being more mass. We will end up having a lot of unused fuel for a variety of reasons, and we just say, yay, great, more mass. But other than that, no, there was nothing put on it just to be mass.
There's no dead weight, in other words.
There's no deliberate dead weight, correct.
One of the chat question came up with how far away is the spacecraft going to be from Earth at impact time?
It's 0.072 astronomical units. That's the number that I remember. I don't remember what happens if you multiply that by 93 million miles, but you guys can do that.
Yep. Okay. I think that answers this question.
Question from Zoom. How do you know how bright this asteroid is magnitude wise?
At the time of impact, it's going to be about 15th magnitude, so it's going to be tough unless you have, tough for a backyard telescope. If you've got something fairly large, sort of 1 meter class, you'll be able to see it. If you have means of taking good, taking precision photometry, give it a try. You might actually see see brightening. Oh, but wait, you can't. Sorry, I left out an important part. On impact day, Didymos is way south of the equator. I think it's down at -30 dec. So
Okay,
you
never mind.
can't see it from where you guys are. So if you have a 1 meter telescope and a boat, and you feel like going down to the Indian Ocean, then you can observe it.
Okay,
But it's
thank you.
coming north, but after impact, a couple weeks before, sorry, a couple weeks after impact, it'll be north of the equator. So it should be observable. You probably won't be able to see anything other than a dot, but it'll certainly be exciting for anybody. I mean, I love the ability to see Didymos with my eyes through an eyepiece. I hope to be on some of the observing runs after impact and measuring the period change, but it's always fun to look at something through an eyepiece.
I have a question. Could the asteroid be pulled back into its orbit after impact? If that makes any sense.
Well, so so Dimorphos, the moonlet that's going around Didymos, is in orbit around Didymos now, and it will stay in orbit around Didymos, but that orbit will change by 1%. That's what we're expecting. The pair of them together is in orbit around the sun, and that orbit will not change at all because we're not giving a large enough impulse to make any difference there. Did that answer your question?
Yes, and once we know exactly how this works and that it will work, will we be able to apply that knowledge to any size asteroid that might be coming at us?
That's the intent. Of course, reality is a lot more complicated than what you'd like to have happen, because remember way back at the beginning, I said there's no such thing as just another asteroid. It means that asteroids are different from each other and lots of different kinds of asteroids. So we're in this funny realm, right? It's in this funny period of time, right? Because 100 years ago, we knew pretty much nothing about asteroids. 100 years from now, we will, I hope, know pretty much everything about all of the near-Earth asteroids. We will have them all identified and mapped, and we will know all the trajectories, and we will have this just pegged, and we will have great knowledge. We will have been to many asteroids. We will understand the mechanics of asteroid surface materials 100 years in the future. Right now, we're in this realm of developing information. We've got partial information. So we're going to learn how one asteroid surface responds to a kinetic impact. Can we immediately jump from that and say, okay, great, all asteroids are going to respond exactly the same way? No, of course we can't do that because there are many different kinds of asteroids. But at the same time we're doing this experiment, we're developing our basic physics understanding, our ability to simulate the mechanics of asteroid surfaces. And we hope to be able to develop, and we're working on this literally right now. I'm writing a paper with the DART team at this moment. If I weren't talking with you, I would be working on this paper probably, of how we do it. What you're talking about is how we extend the results from the DART test to an asteroid, some asteroid in the future that we might discover. A big part of that, I should mention, is that the DART mission is going to be followed by a European mission from the European Space Agency called Hera that will go to the same asteroid system. They're planning to launch in 2024. They'll get there in 2026 and do a full rendezvous, go into orbit, release a couple of CubeSats that will do fantastic things, do a complete comprehensive survey and measure everything there is to know about the Didymos system so that a few years after the fact, we will know exactly what it was that we hit, and that will enable us to refine the results of the test even better because we'll have those precision measurements from Hera. So all of that information combines to give us a gradually improving knowledge of how we can learn from this test and really apply it in a future situation if we have to.
Thank you.
Another one? Oh, sure.
Another question.
I got more
I have another
questions.
question. Are there any missions on the drawing board to try other methods of deflecting asteroids like gravity tractors?
Not well on the drawing board, maybe. Actually, in development, no. Gravity tractor. So for people who haven't heard of gravity tractor before, the basic idea of gravity tractor is you simply use the mass of the spacecraft to gravitationally pull the asteroid. And so the only difficult thing, well, there are two difficult things you have to do. One is that you have to build a spacecraft that is massive enough to actually have a significant amount of gravity. One way of doing that is something called the enhanced gravity tractor, where you build the spacecraft, but then you go to the asteroid and you pick up a boulder from the asteroid. Well, that makes it a lot harder, because now you have to build a spacecraft with the ability to pick up a boulder. So it just got a lot harder. And the other thing you have to do is have a spacecraft that can precision station keep. It has to maintain a distance from the asteroid in exactly the right direction, and do it for many, many decades, because gravity is a very slow force. So you need a propulsion system and a guidance system and all that, and a spacecraft that will continue working for decades. So that's why it's a hard problem. It's an expensive proposition. In a way, it's not something that really needs to be tested, because we know how gravity works. I mean, if you have the spacecraft and the guidance system works and can station keep, it's not like there's any question about whether it will pull hard enough. We know that gravity is going to do that, but it's not something that's a high priority for a full up test. The other kind of technique that's been studied for deflection is when you have a large asteroid. As I said, we know none of the large asteroids that have been discovered is a danger, so this is not going to happen anytime soon. But if you have a large asteroid, or you have a short enough lead time that a kinetic impact is not viable, a technique that's been studied is doing something similar with a large nuclear explosive device. Not to destroy the asteroid, but to kind of do the same thing as the kinetic impactor. You set off the nuclear explosion next to the asteroid, vaporize a layer of material on the hot side, which jets out this way and pushes the asteroid that way. That's also something that can work in theory. It's not something that you would, doing a full up in-flight test of that is not something that you would do lightly, because putting a large nuclear device on the top of a rocket and launching it is not really something that you want to do unless you have a very, very good reason to do it.
Okay,
I had another question if no one else does.
okay.
This will be the last one. Say that this mission and all of the information you find is really knowledgeable and helpful, and you can predict a lot of things. Do you think in the future we would build a rocket and have it just waiting in case this happens? And then, because I'm thinking there would be a time, the time issue would be relevant of how to get it up there to do whatever it's going to do.
Yeah, that is a great question, and it's something that we do worry about, because it's one thing to have the technology available in your head, right, or available in principle. It's another thing entirely to have it literally at the ready, and it is a different set of questions for how much of an investment we collectively want to make in having equipment literally ready on the shelf. We tend not to have launch vehicles that are ready right now. We don't have a spacecraft bus that is ready right now. We don't, a suggestion that has been made is to have the ability to sort of commandeer whatever happens to be in construction right now. Somebody's building a communications satellite. Let's just grab that, turn it into a kinetic impactor and launch it. Well, that's not something we've developed the ability to do. Our kinetic impactor was designed to be a kinetic impactor. You can't just turn one thing into another thing and have it do something else. So, so that is a very important question of how prepared do we need to be? Ideally, the way we would like to be able to do this is to have our asteroid discovery capabilities be good enough that we can discover dangerous objects many years in advance. So we have the lead time to do the development without trying to commandeer something or turn one spacecraft into something that it isn't. So we'd have the time to do the development, launch, apply the deflection, and give that years to wait. So that's why the most important thing that we're pushing next is the Near Earth Object Surveillance Mission and the Near Earth Object Surveyor Telescope. That'll be the next flight mission coming out of the Planetary Defense Coordination Office. That's a space-based thermal infrared telescope that is optimized for finding near-Earth objects And that will give us a really big push toward completion of that congressionally mandated goal. Another thing that will also help is the Vera Rubin Observatory, the Large Synoptic Survey Telescope that is now nearing completion, built by the Department of Energy and the National Science Foundation. That also is going to discover huge numbers of asteroids everywhere in the solar system. So really the best way to make ourselves safer is to develop our survey, our discovery capabilities, so that if we do need to do something, we've got the time to do it.
Right. Thank you.
Thanks.
Great talk.
Yeah. Hey, Tom, I had a question for you too. Wanted to think about how is the loss of Arecibo affecting the ability to be able to detect the asteroids that we want to look for?
Yeah, thanks for asking that. So the loss of Arecibo was so very sad. It just, yeah, people cried, and yeah, it's just a tragedy. Thank goodness nobody was hurt, and it was just loss of property. It doesn't affect our ability to detect asteroids at all, because asteroids are found using wide field optical and infrared telescopes. Radar observations are things that you can do when you know exactly where to point, when you know what you're trying to observe with radar. What radar gives us the ability to do is to characterize the objects, measure accurate shapes and sizes and rotation speeds and things like that. But it does require the object to be very close. And so what the loss of Arecibo did to us is that our range, excuse me, our range over which we could do radar observations of asteroids shrank tremendously. We can still do a lot with the Goldstone radar, and there are studies being conducted to try to figure out what we might do to try and recover some of those capabilities that were lost by Arecibo. But you know, as bad as that was, it doesn't change our ability to discover asteroids at all, because Arecibo was not an asteroid discovery engine. It was an asteroid characterization and study engine.
Okay, great. Anybody else? No? Okay, well, thank you very much, Tom. We really appreciate it. This is really wonderful.
It was a pleasure. Thanks, everybody, and have a good evening.
Okay, thank you very much.
We have the best club.
That's it.
Hi, Dick.